Good evening, friends, and welcome to ESAN Academy. We are into embedded system. We are into understanding all about ARM microprocessor and microcontroller. Week 2 and session 2. So, in the second session, we will continue. The first session we discussed about typical ARM M processor and other ARM architectures and everything. We have not discussed much of the keywords. We will start one by one all the keywords coming on the second session. Quickly we'll go through, and later we'll when we have discussing about software, we will try to link. See, the ARM is tightly coupled, the hardware and software. I cannot differentiate the hardware separate and software separate. There's a very complex. It's tightly coupled. So that's why I'm giving a small idea about hardware today. And tomorrow we will discuss, next session we'll discuss about a little bit of software. Then we will start going one by one. That's the beauty of the way ARM has to be discussed. So let us get into the hardware architecture. Let us continue. Okay, so let us go back. We have seen all this ARM V3s and other things. Let's go to the see here, this is what I told you. See here, this TCM, tightly coupled memory, it was available only on the Cortex R series. And instruction cache, data cache, AXI, master AXI slave, all these things are available only in Cortex R series. They were not available in Cortex M series previously. Now, with the introduction of these things in M series, M7, there's slightly what do you call overlap of M and R. Okay, and this is they add more this type of units in what do you call R5 and R7 and R, nothing more than that. Then let's go to the A series. The A8, there were the only initial things. They came, what you see here, they have a L1 cache and L2 cache memory. And they have a MMU. All those things are there in the thing. Let us go much deeper. This one. Here. Okay, you see that here is much more bigger one, A5 core. So they have, see here, they have a 4 cores inside, and they have a iCache, D and everything. All so many cache for each one, and they have a advanced bus interface, AXI bus interface, and system timer. All those things are built in. So this is called A series. Okay. Now I'll tell you one by one all the things. Okay, so let us first discuss about debug interface. They have something called debug access point. There are 2 types of interface. One is called JTAG. One is called serial wire interface. There are 2. SWD, serial debug. There are 2. And JTAG is a very trick. We have already discussed that. For example, if you take a chip, JTAG is for two purposes. One purpose is very simple. I have a chip. I have one more chip. I connect, I do the circuit. What I do here is I have a test access point or text controller. From here, I give a signal called TDI. From here, there's a signal go to TDO. That goes to TDI. This TDO will come here. You understand now? So, yeah, I connect two chips. This is chip 1, chip 2. Chip 1 is having an interface called TDI. And chip 2 is also having an interface called input called TDI. I connect this TDI to that TDI, and that TDO will come to me directly. So I have two of them. Now, there are two more interfaces called TMS and TCK. See that there are four, TMS, TCK, TDI. But whereas the TMS and TCK is common for both. This can also get the same thing. They are parallel. This is called, see, one input is going to one chip. This is going out and going to thing. This is called DAISY chain mode. This is called DAISY chain mode. Please understand. Why they have it is here is this guy, the controller, is having so many registers. This guy is like a controller. See, please understand, there's a controller, like how we do it previously using microcontroller, using the RTC. You control to I2C or SPI. Like I2C or SPI, this is a controller called JTAG. Please understand, this is a JTAG interface. Like I2C, SPI, this is also serial. This is serial interface. The clock is used to send the data. Okay. TMS will do the mode set. What mode I am going to operate. Now what they do here is, each IC is having an ID. This guy ID may be 1, 2, 3. This guy ID may be 4, 5, 6. So what this guy will do, when I send the ID through the serial, if it is not for him, he will go to the bypass mode. See, let us say I want to access this chip. I will tell this guy, you go bypass. Then this guy will bypass. Whatever he gets, he will pass on to that guy. That means that using one wire, not only two chips, I can have n number of chips like this. Please understand. See, this is all general knowledge. You should understand that. The JTAG called DAISY chain. Comes back. I can have 1, 2, 3, 4, 5, 6. By using a software here, your laptop, I can control all the chips. What I can control? First, understand one thing. This chip is having a core inside. This is also part of the core only. This is also part of the core. I can detach the core, except this. I can detach. That means that physically I can make this silicon not connected to the pins. Now I can make any pin as a 1 or, and this pin as, I read this from this pin. That means that I am writing 1 here, I'm reading 1 from there. That means that I'm checking the circuit. Checking the circuit. So you go and check, you go and search the net. What is JTAG? They will call this as a boundary scan. Boundary scan. What is a boundary scan? That means that they will make sure that all the connections are perfect. So what happened? I will first talk to this controller. and make this pin 1, pin 25. But I know that in my software, I know that IC1, pin number 25 is connected to IC2, pin number 15. This is called netlist. This is called netlist. They'll tell you that what pin is connected to what. Now what they will do, so please understand, it is possible, let us say I have a big board. Where are all your, see, you think that these are all nothing, but this is one that lot of companies now in Chennai, in Bangalore, they manufacture the boards. And for the boards, you suppose write the software to check these things. There's a huge area is available. If you say that I know JTAG, that company will recruit you. There's a manufacturing company. If you tell them I know JTAG, they will do the thing. Because every board, what they will do here is, this is a JTAG. 5 pins. 1, 2, 3, 4. There was one more pin called reset. T reset. TRST. T means test. The T represents test. Test data out. Test data in. Like that. Test data out. Test data in. Going to in or here. So what I can do with the JTAG is, this is what the JTAG was born. But later what they have done was, they have made this is called X test. That means that I am doing the external test. The one more thing is called in test. See, I don't know whether you use it or not, but you should know that what that JTAG does. This is very important. The word JTAG, even if you don't use it, knowing the technology is very important for the embedded engineer. Nobody will use JTAG except you. You know one thing, using JTAG, I can run my software step by step. Okay. It's very, very important. Now using JTAG, I can able to do the in test. When you do the in test, I will give the command to the CPU and make the control. Please understand, so far I have discussed you, the CPU is controlled by the control unit. Control unit gets the opcode from your memory. And CPU access the opcode, and then control unit does the operation. Now, without this, let us assume that the chip is memory. Your CPU is not accessing the memory. Then you are gone. You are dead. Let us assume that your CPU is not accessing the memory. You are dead. You cannot do anything. That time, using JTAG, I write and read. Let us assume that I write 55. I write data 55. 10, 10, 10, 10. I read 54. Sorry, 55 minutes. 01, 01, 01, 01. I write 55. I read 54. What it means? You will easily come to a conclusion. This is some problem with the D0. Then I will go to the multimeter and check what is problem with the D4. Oh God, there is a connection is out. Can make the connection, things will work. These are the huge debugging using JTAG. You can do single stepping. I can put the breakpoint here. We will discuss about later in the software what is called breakpoint and what is called hardware breakpoint. Software breakpoint and hardware breakpoint. There are so many things are there in that debugging. So what we do here is using the JTAG controller, using the tab or debug access point, using the JTAG controller, I can write anything here. I can do wonders. That means that even CPU is dead, I can able to debug with the JTAG controller. Let us assume that there's a hardware engineer who designed the board. And he tested that power is coming, clock is coming, everything is coming. But he has given the board to you, to firmware engineer. How do you debug? These are the tricks. Okay. One is JTAG, but you know that JTAG is quite expensive. So what these people did, who? Your ARM people, to make your debug easier, they had one more interface for the debug access point. It's called soft serial wire debug, single wire debug, only one wire. I can able to send and receive back. What I can do here is, I will be able to serially send. They're given a spec, go and read the data sheet. They're given you all the thing, how do you start of the packet, what register access, everything. I can control this guy like what the JTAG does. I can do the same thing. But what is the difference between these two? JTAG intended originally for boundary scan. That means that the circuit can be tested also, which is not possible here. This is only for debugging your own thing, your processor. Okay, you get softwares to control this. So since I'm discussing the hardware, I am telling you that what is this this one. Then, so we have two things: the debug. We have JTAG interface, 5 wires. One is TMS, TCK clock, and TDI, TDO, and TRST. Like a SPI, you have 4: master out, slave in, master in, slave out, SS, slave select, and clock, SCK. Like I2C, SDA, SCK. You have two things. Like that, JTAG has a 5 interface. And SWD had 2 interface. Data and clock. All are synchronous. Nothing is asynchronous. Everything is synchronous. Now what you do is, like, how do you access the RTC? How do you access the timer? How do you access the SD card? It's like that. This debug access port is having some registers. You access them using your software here. Then you do that. You can able to control the whole controller. It's all very interesting projects. The thing is that these type of things will take you into the big MNCs. They do this type of work. If you say that I know JTAG thoroughly, I know serial controller, single wire controller perfectly, you're done. These are things. See, the moment you use the word JTAG in the interview, big companies, not small companies, don't even understand about JTAG because they don't do that. Big companies. If you use that, I've debugged, you used one word in your resume. I've used JTAG to debug. I do GDB, GNU debugger, GDB, using JTAG. That's it. That's it. That guy will pick you up because very few people could write in resume the word called JTAG. Understood? That's a trick. Now, the next one is called bus. What is a bus? Bus is a common one. That means that set of wires, address, write, read, same thing. Data, all those things. Understood? Now, when you have a bus, who is going to be the master of the bus? There's something called bus master. That's a trick. So there are 2 types of people we discussed actually. One is 2 types of people can be a bus master. One is your microprocessor. Other one is your DMA. There are two type of people can be your bus master. So if you have a bus, then we know that the microprocessor will have a request and acknowledgement. That way this guy will grab the bus. But now that's not always true. The problem is nowadays I can have multiple processors. See here, I may be having a CPU 1, CPU 2, CPU 3, CPU 4. I have a multiple CPUs and I have a multiple controllers. The beauty is that I say this is RTC. There's one RTC. This guy also want to read the RTC. This guy also want to read the RTC. All the four want to access the RTC. Okay, then it's a problem. So what happened? There is somebody here called bus arbiter. What's that? Bus arbiter. Understand? What happened? There's a bus, there's a signal through which all the people can request him, whoever want the bus. So think of why, what is the difference between what we previously discussed, a microprocessor and the CPU bus? That bus is tightly coupled. You have one microprocessor, you have all the peoples of slave. We call this as a master, this as a slave. And only exception is DMA. But you cannot connect general peripherals like that. So they have a bus arbiter. Now, this guy will be connecting, talking to them like this. And whoever wanted to access the controller, but please understand all the people will have a memory separately. This guy will be using these memories. They have a separate memory. They have. That's what I told you now, that TCM, tightly coupled memory. They have their own memory there. They also have their own cache memory. Please don't worry, only today. Only today I will explain this and leave it. From tomorrow we get into the softwares, please. So next class. But I have to tell you that what is the way your embedded system is going on. And these are all tomorrow when you go and see the read the documents, when you see any PowerPoint, you will understand this, what is going on. Because they will explain you at the top level. They don't explain you at the very bottom level what is this thing. That's the only difference what I'm trying to make is that there's a huge treasure on net. But you are not able to access that. That's a problem. You have a huge treasure on net. I am helping you to make a bridge. I single person Balaji cannot replace the entire treasure stuff. But the problem is I enable you to access the treasure. The problem is here, those who put the documents on the net, who puts the PowerPoints on the net, who puts the videos on YouTube, they assume that you are at this level. To reach that level, it may take you 3 to 4 years. Now, I am trying to minimize it to 3 to 4 months, such a way that you will be able to get into the thing. So, if you don't access the net, then you are gone. You have so much of material. Now you want to confuse. Now I want you to confuse. And you can ask me, sir, I have seen the material. I'm not able to understand. Can you explain to me? I will do that. Because now you are at a good stage. By keep on attending the lecture, now you are understanding that now you know what is bus. Now I'll explain to you that what are the thing about buses. The bus means, as I told you, that there are devices which are all slave, where you write and read your RTC controllers, your display controllers. You have so many controllers where you want to do read and write. Am I right? Now, timer. So many things. SPI controller, I2C controller. You will access from here and do that. This becomes slave. Now you have 4 masters. Now any master can request the bus. And suppose the thing is, I have a memory here. RAM. I have a RAM here. I want all the 4 people to commonly access the RAM. Think of it. Now, all these guys are slow. So clock. Whereas this guy is a fast. I don't want to waste the time. What they have done is, if they make everything fast, I cannot access this. If you make everything slow, I'm going to access the RAM slower. So what they have done is, they made a 2 bus. This is called high speed. Where all the high speed devices are connected. From here, there'll be a bridge which will connect to all the low speed devices. Generally, all the peripherals are slow speed. That's why they call this as a APB. Okay. And this is called AHP or ASP. ARM system architecture, ARM system bus or ARM high speed bus. This ARM peripheral bus. So you see here, there's a problem. Do you see what is the problem now here? Can you tell me a problem here? One problem. Only one CPU can get the bus. Let us say that the CPU 1 wanted to access the I2C. And CPU 2 wanted to access the timer. And CPU 3 wanted to access the display. CPU 4 wanted to access RTC. All the 4 wanted to have access different controllers. But unfortunately, what happened was there's only one bus. So they thought what to do. So they brought a superb, nice mechanism called, because somebody asked, I'm just replaying now. They brought a bus called AXI. Here, so many things are there. This is called bus matrix. The advantage is here, when this guy is talking to this guy, this is AXI slave devices. This is all AXI masters. So this is a new concept. It's a new concept where when this guy is accessing this guy can access this guy. There's no common bus. This is actually called different name. This is actually called what? It's a different name. It's called NOC. Network of chips. They're actually networking all the buses. Okay. That's the level exactly like you have an Ethernet switch. The Ethernet, there are 2 things are there. One is called hub, one is called switch. Hub is at the time only one guy can access, whereas switch all the people can access. So that's why this is called NOC, network of chips. That's a very, very important concept here. This is what somebody asked me, what is called bus matrix. Now this, see, till yesterday, these things are the high end. These things are very high end. Top companies, only that, only that mainframe or your supercomputer uses this. Today, your ARM, your this guy, Intel, everybody brought into your thing. You cannot say that you don't know. You don't know that. No, you should know that. That's why that diagram has represents that word called this one. What do you call? Bus. That means that you have so many buses. That is, you have a buses called AHP or AHP Lite. Or ASP or APB or AXI. All of them are called AMBA. All of them are called advanced microprocessor bus. So AMBA is not a single bus. AMBA is not a single bus. Each bus provide you more details. Or I can, when we start doing the ARM, I'll try to put all what are the signals are there. Nothing. The trick is that if you do AHP, what is the difference between this? One is clock. This is slow clock. It's a fast clock. That's a very first one. Second one is sometime this will go by 32-bit. This will go by 64-bit. So I'll do twice the speed. And third one is, one thing, when you access a memory, you always do this. You give address. You give always address. Then you give write or read. And you give data, you get data. Now, in this mode, they have something called burst mode. I'm just trying to explain to you that what are all the differences, why they have so many buses. Each one is having his own advantage. Ultimately, it's what they wanted, speed. Ultimately, what they want, speed. And less cost. That's why all the confusions are because of this. So now this is what happened. Okay, so in the burst mode, once I give an address, then if I start giving a clock, every clock I get one data. I do not have to give address. That memory will automatically, the controller will increment the address and get the data. That is the advantage of this bus AHP. That is called burst mode. I can fill the data very fast. Why I need it? For example, I'll tell you the very nice thing. I have a main memory. I have a CPU. And this guy is slow. This guy is fast. So I give address, I give data, everything. This guy will be giving very slowly. So what we have done is, we have added one guy called cache memory. This is a fast. This is a fast memory. Initial days, this cache memory used to be outside the chip. Okay, outside the chip. Then what they have done, what this guy will do, the cache memory, using something called cache controller. All the transaction this guy will monitor. Actually, you can call this as a spy. He's a spy. He will monitor all the things. Understood? Then, if you are from 1000, if you access 75, he will also put 1075. The next time if you are accessing 1000, he will give it. But this guy is fast. This guy is slow. This guy will do it. Now, what we will do here is, we have a unit called fetch unit. What that guy will do, he will do the burst access. Every clock one data from main memory that will get transferred to the cache memory. That's what the fetch unit will do. So next time onwards, the microprocessor will take from the cache, your software will be faster. I'm just explaining to that why they use the burst mode. You may not be able to understand, it may confuse you. I don't mind. I'm trying to tell you that what is AHP. When you get into the ARM, automatically people will ask about what is the architecture, AHP, APB. If you are going to do only the top level software, no problem. If you try to understand, some of you could be trying to understand what is the architecture. You open the data sheet, you open the buses, you will be hearing the word called AHP, APB, ASB, AXI, all these things. Okay, now you go and read it. You will try to understand them. I also will give a lot of pointers, but not to get confused. Now what they have done was the chip. They've done a beauty. What they have done, unfortunately, this CPU will become faster still. So the cache itself becomes slower. Okay. So what they have done, they put a cache to cache. This is faster than this guy. Understood? This is the slowest. This is slower. This is slow. This is fast. Now, they found out that still this becomes fastest, the CPU. This cache becomes slower. So they put cache to cache. See that this is a very slow memory, very slow, very, very slow. You have one more memory is there, that is forget about, that is called storage. That's why we copy the storage into the RAM from here. So this is the way it goes. This is called L1, L2, L3. L1 will be very low, but fastest. L2 will be slightly more than L1, but it will be slightly slower. L3 will be more than L2. And this is called main memory. This is your DRAM. Now what happened? They put all these things inside a single chip. Inside a single chip. If you take the latest ARM processors, they have a ARM core is there. They have L1, L2, L3, all in the single ARM processor. They have it. Please. This is called core. Don't get confused with the core and the processor. Okay. That means that your data is getting copied at so many places. Why? They wanted to execute things faster. Unfortunately, M1, M3, M4 do not have this cache. If you have a cache memory, you cannot calculate how fast it is doing because it may do it from here or it go there. Sometime, you know one thing, there is something is there. I write a program, int x is equal to 45. I write. Do you want to write here? I want to keep it only here. That is called write through. Or write back. Write through means I don't bother about the controller. I will write on the main memory. Write through means I will write that, I will write here also. Let us say I'm writing at the X is maybe 2000. At 2000, I write 45. So I will write on the main memory as well as it will be copied here also at 2000. So next time the cache access will give. Write back means I don't write here. This could be at 98. But I write only here, I read it from. I will never update the main memory. When I will do that? By chance, I overwrite with some other data. That time I write it. Otherwise, I will not write. This is called write back. So please understand, write through means I will bypass the controller and write. Write back means I will copy it only in the cache, not at the main. I will not update. These two will be different. These two will be different. So you have to make sure that in the MMU, you have to say that don't, let's say your peripheral, RTC and dot, anything. You should tell them that don't access this area cacheable, non-cacheable. You know that they have given a memory map. The memory map they have given from 4000 to 6000. This range is non-cacheable. So you write everything, it will not be in the cache. That will go in directly. Now what happened? The trick is that sometime you have a ROM, you have a RAM, you have a microprocessor. You access the code here. You access the data here. Understood? This is called code, this is called data. Now I have a separate cache for code. And separate cache for data. Okay, I have two types of cache. The advantage is normally the code will be in sequential. It will have the more hit. I don't want that has to be, if I have a single cache, when I access the data, that guy will overwrite that guy. I will lose the cache memory. So we have this type of cache. So what people do here is the processors nowadays, I have a multiple processor, you have dual processor. I have a cache. I have a cache. I have a local memory, TCM. I have a bus. I have a main memory. The main memory is common for both. But these two are common to the local. So if I don't have this here, I will go there and do that. That way I'll be able to save my performance improvement. These are all, I told you now, these are all previously not in this one, microcontrollers. Now your Cortex M7 itself have all of them. It has TCM, it has cache. And you know that slowly they replace M0 with M3. Then M3 is gone, M4 is come. I know very clearly by next year, M7 will go out, M7 will come in. So you have to know all these things. Okay. If you want to be an embedded engineer, if you want to be a software engineer, you need not to know all these things. Now I will tell you one more important thing, which is available only in A series, not in M or R series. Both don't have. Only this series, A series, have a unit called MMU. So your ARM V87. See, understand one thing. I use ARM V7A. That's called A series. R means R series, M means M series. This access here, address. This is address. This address is called virtual address. Please understand, this address is called virtual address. One more thing I forgot to tell you, both R and M, they have addresses only 32-bit. 32-bit address. But this ARM V series, okay, can have 32. This V7. V8 have 40 and 44 also. That means that 2 power 32 means 4 gig. 2 power 40 means 1 tera. 2 power 44 means 16 tera. See that? I can access now 16 terabytes of memory, please. Now, the memory out of this guy is called physical address. Is called physical RAM. The trick is assuming that I have a 32-bit address, 2 power 32. I can access 4G. But the RAM could be only 1G. But still, from a software, you can access the 4G. So virtually, 4G is possible. But through the this one, physically, you have only 1G. Who converts the virtual address to physical address is this MMU. This guy has a tables. That's why I told you that MPU. In your Cortex M series and R series, you have a MPU that's called Memory Protection Unit. That does not convert the address to physical. What that guy will do that, hey, I have a memory here. I have a RAM here. Who can access? System mode or user mode or some other privilege can access that or not. Inter-privilege or so many. That tomorrow, next class, we'll discuss about all the privilege modes. Now, this guy will block or non-block access. But whereas in this case, MMU case, this will be very interesting when we discuss about embedded Linux. That time we will discuss about very thoroughly about all the MMU, how the kernel is using the MMU or not. Is it clear? So I have address. I have physical address. This is also address. This is physical. RAM I have, but the address given by the your processor is a virtual address. Now what they do here is, if you access more address, they will have the space in your storage, the remaining memory. The remaining 3G, have it on, let's say, in the storage, I'll have a 4G. I'll write it in the top, sorry. I have a storage. I have a 4G. I will, when you access memory, if it's not available here, then I will swap from here to here and here to here. This is called swapping. This is called virtual memory. This is called physical memory. This is called virtual address. Please don't confuse between virtual address and physical address. They call VA and PA. If you try to understand about Linux device driver and all, you'll be accessing only this when you wanted to go. That's the thing. Now this is called what? Virtual memory. This is called physical memory. So virtual memory is actually a storage. Okay. And your physical memory. This type of units are available in your A series. This is wanted by your Linux operating system. If you don't have a MMU, then Linux cannot work on that. But RTOS can work. I can run the RTOS in M series. I can run the RTOS in R series. But I cannot run what? Linux on M CPU and R CPU. You know that both mobile phones and laptops, Linux PCs, okay, they use Linux kernel. Whoever uses Linux kernel, they need this A series. That's why all your mobile phones are using A series. They never use the R or M series. Any doubts? I have fairly explained the hardware level. They're all same microprocessing. They added so many extra units. Nothing more than that. They became very simple. They started with very simple. Explain about 1G. Fine. Okay. I thought I'll avoid it. Okay, very good. I exactly where I am escaping, and you have asked. If you don't get confused, I don't mind to explain. Okay, I'll explain that. Since somebody has asked. If somebody has asked, I would have. Then I'll tell you. I frankly tell you, this is all slightly more confusing. That's why I didn't explain that. Yeah, there are two things are very perfect. What need MMU when the processor can use the actual address itself? Oh, super. There are two things. Now I'll explain this very clear. I have a microprocessor and I have a memory. I do multitasking. When I do multitasking, I load first word from the hard disk storage using the controller. I load the word here. Word occupied the memory. Now I load Excel. Now I load the Chrome browser. If we started loading one by one all the applications, okay, my local RAM is full. But I know that my microprocessor will execute only one at a time. My microprocessor cannot execute all the things at a time. He will execute only one at a time. So what we have done is, we have created a space in the hard disk called swap space. Okay. Now, let us assume this guy occupy 1G. This guy occupy 512. This guy occupy another 512, whatever it is. Now, when I'm trying to load one more software, I know that I'm not using kernel. This kernel is having a scheduler. The scheduler knows that which one is active. Oh, this one is active, word. What that guy will do, he will swap the Excel here, the RAM. Now free the space. Then there you have another application, let's say Windows Media Player. That I will load. You understand? Whichever I use it, I have a less memory, but I want to run multiple tasks. I cannot do that. But the OS gives you the ability, which are all called active, will be here on the RAM, which are passive, will be going to the thing. But this guy, MMU, knows that your address is where it is available. Understood? Why this is required is, you have been given a 32-bit. So your software will assume that entire 4G is available to you. So your software thinks that you have entire 4G is available to you. But it is not that I have only 1G. So what that guy will do? So let's say if I run about 5 softwares, each software thinks that I have entire 32-bit. They do not differentiate. Each software thinks that they have the entire memory is for them. But what the MMU does, when you access the memory, if it is not available here, the RAM, he will give an interrupt. That's why you call segmentation fault. This will be handled by somebody. Then that guy will swap the memory from here to here. Then allow you to access. So many things are happening. I have taken a class for the previous batch. That is weekend batch. I will share this last class videos to you. You will be able to understand. Now, what is happening is, here I have a memory. The swap space, I will swap it and get it back. So this guy knows that where it is available on a swap, where it is available here. These are all done by your kernel has 4 things. One is called process manager. The next one is called memory manager. The next one is called disk manager. The network is called network manager. All the people are accessing the hardware. Below them, they all going through the driver, device driver. Not this memory manager, this guy, sorry. Goes to the peripherals. So this whole part is called kernel. So this was Linux kernel. I'll explain this more deep. Or in the ARM class itself, if you've done everything, if you ask sometime, I can explain all the process, everything, how the scheduler works, how the preemptive multitasking work, how the cooperative multitasking work. I'll discuss more. How the memory manager is converting a virtual address to physical address. How the tables are filled. What is actually, they don't call disk manager, they call VFS, virtual file system. What is VFS? How the network manager works. All the things are very interesting. But I can discuss everything, man. But I know that if you're not good at ESP, all are waste. That is what I started the ESP. If you're not good at ESP, if you don't understand the ESP, then you don't enjoy these things. That's why I've not taken these things. I'll share the batch, all the batches videos to all the people on the our group, ESP group. And maybe the 8th batch, the last few classes, I have it. Some of you can even mark it up what is there on the lectures. Anyway, that problem I solved in coming January. You know that I'm marking that what day, what class. I already do the predetermination. Previously, I did not know how much time it will take, how much time you will be able to understand. Now I have a very good clarity. When I'm taking class for you people, it's the first time. I did not know that how much time you will take. That's the thing. Even now, I was prepared more, but I could not deliver more. The 2 hours only this much is possible. I'll do one thing. Last class we discussed why. Today we discussed a little bit about hardware architecture. I know that you might have got confused, but that's fine. But you have got something. That something is very important for me. Maybe 5 minutes or 10 minutes worth. You would have got 10 minutes worth. That is enough. Then, next class, we discuss about software. All registers, other architecture, what is a standard. Then we will discuss about system. This together. Then you will try to understand. The problem is ARM is a very collective. If you together understand, you will do wonders. So I think I've fairly explained, but more these things that we will coming days we will do that. If you want, one day we can be able to discuss about kernel itself. What exactly is a kernel for 2 hours? That time we will understand about why. If somebody asks why I need a memory, I'll explain very clearly. I'll explain much more clarity. If you give me 2 hours, full 2 hours, only for scheduler, system management, process management, sorry. I have not explained a word called thread. I'll explain tomorrow. Next class, I'll explain about what is called thread. People have to understand about threads. Okay. What is process? What is thread? So many things are there. The problem is you are preoccupied with so many other things. That's the thing. If you're going to be on this line, all these things will be very useful. First, spend a time doing a ESP. How much program you do, that much you will like these things. You will also grow on this. If you stop programming, these things are information to you. No use. Any other doubts?